Number 2 on the torque worksheet, we have a pole that is attached to this wall and it's being held up by a rope, and there's a sign hanging off the end of it. And we're given the mass of the pole, the mass of the sign, we're given the length of the pole, and what else? This angle, it's 30 degrees. So let's just put this in here. So these problems, you start by doing a free body diagram for the object that is rotating or could rotate. So in this problem here, what is the object that could rotate? There's no rotation here, but we have something that could rotate. What is it? Is it the sign? No. Is it the wall? No. Is it the pole? Yes. So we're gonna do a free body diagram for the pole. Now, since you guys are new at torque, look, I'm going to tell you where to put the axis. Put the axis in this problem over here where the beam or where the pole connects to the wall, right? Because that's a good spot for a couple of reasons. One, if you came up to this rope here and you cut the rope, what would happen is the pole would rotate, pivoting from that point right there. Okay? But the real answer is, the real reason we're putting the axis right here is because there's forces on the pole at the wall, right? The wall has to be holding the pole up and exerting a force on it horizontally. And in reality, those two forces are one force at an angle, you know, because like without a vertical force, if there was no vertical force holding up the pole, what would the pole do? It would fall. If there was no horizontal force acting on the pole would break through the wall, right? So in reality, those two forces are one force at an angle, but we don't know anything about those forces. So what we do is we put the axis at that point, because remember, forces on the axis cause no torque. So they won't appear. Okay. So anyway, that's where the axis goes, because then a force on the axis causes no torque. Those forces where the pole touches the wall will not appear in our summing of the torques. All right, so what I'm going to do, so remember this diagram, I'm going to do a free body diagram for the pole. So I'm going to erase this, and this next thing here, this represents the pole. So first thing you do is you label all the forces acting on the pole. So what do we have happening here at the end of the pole? What's hanging off the end of the pole? The sign, and we have the mass of the sign right here. You know what the worksheet is using 10 for gravity? Should we just use 10 for gravity so the answer matches? Okay, so 10 for gravity. If the sign is 75 kilograms, well, 75 times 10 would be 750 newtons, right? That's mg for the sign. That's a force on the pole. Would everybody agree with that? A sign hanging off the end is a force on the pole. Okay, we have a rope. We have a rope like this. Ooh, that's not very straight. Let's do that again. We have a rope that's going like this at a 30-degree angle, like that. And then what else do we have? Oh, tension. This is what we're solving for. We're solving for that tension. And then the pole itself, right? Notice the problem gives us a pole of mass 15 kilograms. So where do we put the weight of the pole? Directly in the center, at the center of mass. So 15 times 10 is 150. What else? And then as I said, there has to be, over here where the pole touches the wall, there has to be a vertical force. We'll call this Fy. And then there has to be a horizontal force, right? Because otherwise the wall would slip. If not for Fy, the pole would slip off the wall. And then if not for Fx, the pole would break through the wall, right? But what we're going to do is we're going to put the axis over here, and then that way Fx and Fy won't matter, because forces on the axis cause no torques. Okay, dudes, what's the one tricky thing that there's one thing that makes this problem tricky. Which force is it? The tension. Because why? It's at an angle. It's at a 30-degree angle. So now look, let's put our distances in here. So I'm going to do this in red. Let's get red out. Scoot that over. So we measure distances from the axis. Ready? So like right here, that's the axis. So they tell us in the problem the length of the pole is 1.5 meters. So 1.5 meters, that's the length of the whole pole, like that. Now, so what would be, oh, they also tell us to the rope, which is right there, is 1 meter. So this distance there is 1. And then how about the distance to the middle, to right here? 0.75. This would be 0.75 meters to the middle. Okay? And we always measure distances from the axis. Now, you guys haven't seen problem 1 yet because I did that last period, but you're going to watch the video, right? So in problem 1, we came across this situation. So look, here's the problem. Our axis is right here. Here's the axis. If you go over to the axis, if you go over to the tension, is that perpendicular to the tension? Is this distance right here, is that perpendicular to the tension? No. So how do we get a perpendicular distance? Well, what you can do is you go like this. Extend the tension up, and you can draw a perpendicular distance. So this distance right here, that's the perpendicular distance to the tension. Does that make sense? Okay. Now how do we get that? Well, look, we can solve for what that distance is by using trig. So if you look at sine, so we have a triangle here. Look at, right here is a triangle. So if we do sine of 30, so sine of 30, what's sine? Opposite over hypotenuse. So what's opposite the 30? That's our lever arm, which is r, right? So r, and then what's the hypotenuse? The hypotenuse is 1, right? That's 1 meter. So r is going to be sine 30 times 1 meter, which is 0.5. So the lever arm for the tension is 0.5 meters, right? So you just got to remember, what's the definition of lever arm? The definition of lever arm is its perpendicular distance from axis to force. So you have to draw that in. You go, okay, here's the force, there's the force. Perpendicular from the axis would be this. And then you got a triangle, and you can solve for it. So we now have the lever arm for tension. And then the rest of the problem is not that bad. Okay? So let's do the rest of it. Okay, so how many torques are acting on this pole? How many torques? We got 1 torque, 2 torque, 3 torques. All right, clockwise, counterclockwise. What's this guy doing? Clockwise or counterclockwise? Clockwise. What's this guy doing? Clockwise, and then this guy is counterclockwise. So let's say that clockwise is plus, counterclockwise is minus, and then now we sum the torques. We're going to sum the torques up. I'll do it up here at the top. Okay, so let's start with the positive torques. All right, so summing the torques, starting with this positive dude. All right, so 750 is the force. Okay, what's the perpendicular distance to that force from the axis? So let's see, from the axis is over here. What's this distance? 1.5. Is that perpendicular? Yep, so we're good. 1.5. These guys right here are perpendicular. They're good. Okay. Next torque is a positive torque because it's clockwise. Okay, so this 150 right here. So we go 150. Okay, what's the distance for that 150? From the axis. So from the axis over to that force is what? 0.75. Are they perpendicular? Yes. Okay, so that's good. And then for our last torque, we go minus T. That's the force. Now, what's the perpendicular distance to that force? The perpendicular distance, we solved for it, is 0.5 meters. In this class, the torques will always cancel, which means the object won't rotate. This pole is not rotating, so the torques are canceling. If the torques cancel, the object does not rotate, or I should say does not have an angular acceleration. So now the only thing missing in that equation is what? Tension. Notice that these guys did not appear. The force at the wall did not appear because we put our axis over there. Okay, so you solve this for tension and you get what? Like 2,000. What's the answer on the worksheet? 2,000. Is that what it comes out to be? I think it's, hold on. Oh, he rounded up, right? I think it comes out as 2,475. Yeah. So the guy who wrote this worksheet rounded it, so it's actually 2,475.